There is a place on Earth where the land itself becomes a weapon, not in the way that cliffs are dangerous or oceans are dangerous or volcanoes are dangerous, where the threat is obvious and visible, and the thing trying to kill you announces itself loudly before it does the job. This place is different. It looks, at first glance, like nothing at all. It looks like absence, like the world simply forgot to put anything here. No trees, no rivers, no grass, no shade. In some stretches, no sound except the wind, and even the wind feels like it is made of something other than air, something older and less forgiving, something that has been traveling across nothing for so long that it has forgotten what it is like to touch something alive. This place is the Namib Desert, and it kills more animals than any predator on Earth, not through violence, not through speed or strength or tooth or claw. It kills through something more fundamental than any of those things. It kills through the simple, absolute, almost philosophical fact of its own nature. It is the oldest desert on Earth. It has been a desert for somewhere between 55 and 80 million years, depending on who you ask and which geological evidence you are willing to trust. For context, that means the Namib was a desert before the dinosaurs were finished dying, before the grass itself evolved as a plant form, before the Himalayas were mountains. The Namib was already here, already dry, already ancient, already working on the long, slow project of becoming one of the most extreme environments that life has ever had to contend with. And life has contended with it. That is the thing. That is the story that most people never hear, because the story that most people hear about deserts is the story of absence, the story of nothing, the story of a place where life gave up and went somewhere else. But the Namib did not drive life away. It did something more extraordinary than that. It forced life to become something new, something that should not be able to exist but does, something that looked at 55 million years of heat and dryness and sand and coastal fog and said, "Fine, I will work with that," and then proceeded to do exactly that in ways that will make you question everything you think you know about what living things are capable of. Subscribe right now if you want to see the world the way it actually is, the real thing, the deep thing, the version that makes your jaw drop and your brain recalibrate, and your sense of what is possible on this planet expand in ways you were not expecting when you sat down to watch this. Let's go. The Namib stretches along the Atlantic coast of southern Africa for roughly 2,000 kilometers, running from the Olifants River in South Africa, northward through Namibia and into the southern reaches of Angola. It is not a wide desert, not in the way that the Sahara is wide or the Gobi is wide. The Namib is a coastal desert, compressed between the cold Atlantic Ocean to the west and the inland plateau to the east, and in most places, it is no more than 160 kilometers from the ocean to its eastern edge. But what it lacks in width, it makes up for in character, because in that relatively narrow strip of coastal terrain, the Namib contains more distinct sub-environments, more specialized ecological zones, more bizarre and specific and extraordinary adaptations than deserts 10 times its size. The reason the Namib exists at all is the ocean. Specifically, it is the Benguela Current, the cold upwelling of deep Antarctic water that runs northward along the southwest coast of Africa and transforms the climate of everything it touches. Cold water off a warm coast creates fog. It creates this because the warm, moisture-laden air that flows in off the ocean encounters the cold surface water and cools rapidly, dropping its moisture not as rain, but as fog, as a dense marine layer that rolls in off the Atlantic in the mornings and pushes inland across the coastal desert before the heat of the day burns it off. And this fog, this thin, inadequate, frustrating thing that is not rain and cannot fill a river and cannot water a crop and cannot quench the thirst of a large mammal in the way that rain can, this fog is the reason the Namib is alive at all. This fog is the water source. This fog is what everything is built around. This fog is the single most important meteorological fact in an environment where the meteorological facts are essentially the only facts that matter. Some parts of the Namib receive less than 10 millimeters of rainfall per year. Some years, they receive none at all. There are weather stations in the central Namib that have recorded zero measurable precipitation for years at a stretch. But on those same days when no rain has fallen in 2 years, the fog comes in the morning. It settles on every surface. It coats every rock, and every grain of sand, and every blade of whatever it is that passes for vegetation in this landscape. And then it is gone. And everything that lives in the Namib has figured out, over millions of years of brutal evolutionary trial and error, exactly how to grab that fog before it disappears. Let me start with the beetle, because the beetle is where this story becomes something that stops you completely. The Namib desert beetle, specifically Stenocara gracilipes, is a small black beetle that lives in the coastal fog belt of the Namib, and it has solved the problem of getting water in a fog desert in a way that NASA has studied, that materials scientists have reverse engineered, that architects of buildings in dry climates have tried to replicate. On the mornings when the fog rolls in, the beetle does something that looks, at first glance, like nothing at all. It climbs to the top of a sand dune. It positions itself facing the wind. It tilts its body at an angle, head down, rear end up, and it waits. What happens next is physics, but physics that took millions of years of evolution to figure out. The beetle's back is covered in a pattern of tiny bumps and troughs. The bumps have hydrophilic tips, meaning they attract water. The troughs between the bumps are coated with a hydrophobic waxy surface, meaning they repel water. When the fog blows across the beetle's back, microscopic water droplets from the fog land on the hydrophilic bumps and begin to coalesce. They grow larger, as more droplets collect and merge, and when they grow large enough, the weight of the droplet overcomes the surface tension that is holding it on the hydrophilic bump, and it rolls. It rolls along the hydrophobic trough, gathering more water as it goes, running down the slope of the beetle's tilted back, all the way to its mouth, where it drinks. This beetle is harvesting water from fog using a system of nanotopography on its own body surface. It is drinking the air, and it collects enough water this way to survive in one of the driest places on Earth, generating a droplet that can constitute up to 40% of its body weight in a single fog event. When researchers at MIT and other institutions looked at this beetle under electron microscopes and understood what was happening, they realized that the same principle could be applied to water collection structures in dry climates, buildings and nets and surfaces designed with the same alternating hydrophilic and hydrophobic geometry. The beetle had already solved the engineering problem. It had been solved for millions of years. The humans just needed to look carefully enough at the beetle's back to read the solution. But the beetle is only the beginning, because there is another creature in the Namib that has solved the water problem differently, solved it in a way that is even more visually extraordinary, even more immediately, viscerally, undeniably strange. The Namaqua chameleon is a lizard that lives in the coastal Namib, and unlike most lizards, which try to avoid the morning fog, because wet is cold, and cold lizards cannot move, and a lizard that cannot move is a dead lizard, the Namaqua chameleon runs toward the fog. It positions itself perpendicular to the wind, flattening its body to present the maximum possible surface area to the incoming moisture. Its skin, already remarkable for its color-changing abilities, has a texture that facilitates condensation. The chameleon essentially becomes a fog collection surface. Droplets form on its body, run down its scales, accumulate at the corners of its mouth, and are swallowed. It drinks its own skin. It harvests the air with its body. This is not what chameleons are supposed to do. Chameleons in other environments do not do this. The Namaqua chameleon developed this behavior specifically in response to the specific conditions of the Namib, specifically because of the fog and the absence of any other reliable water source. It is a behavioral adaptation as remarkable as a physical one, because the chameleon did not evolve a new organ or a new body structure. It evolved a new behavior, a new way of using the body it already had, in response to the demands of a particular environment. It learned, in the slow evolutionary sense of that word, to do something that its relatives in other environments never needed to learn. Now I want to take you deeper into the Namib. I want to take you away from the coast and the fog belt, and into the interior, into the part of the Namib that does not even get the fog, the part that is just sand and heat and almost nothing else, because this is where the desert becomes most extreme, and where the adaptations become most extraordinary, and where the story of how life survives in the world's oldest desert becomes almost incomprehensible. The sand dunes of the central Namib are the tallest sand dunes in the world. Sossusvlei, in the heart of the Namib-Naukluft National Park, contains dunes that rise to 380 meters above the surrounding plain. 380 meters. That is taller than the Chrysler Building. These are not rolling hills of sand. These are mountains of sand, massive orange and red formations sculpted by the southerly winds into shapes of almost architectural precision, with sharp ridgelines called slip faces on their lee sides where the sand cascades in thin streams like dry waterfalls, and sweeping curved bases that spread across the desert floor like the roots of enormous trees. The color of the dunes is the result of iron oxide, rust, coating the individual sand grains. The older the sand, the more oxidized it is, and the more oxidized it is, the deeper and richer the red. The youngest sand, the sand that has most recently been deposited, is pale and cream-colored. The oldest sand, the sand that has been sitting in these dunes for thousands of years, is a deep brick red that glows in the early morning and late afternoon light, like something that is generating its own illumination from inside. At sunrise, when the low light hits the face of a dune, and the shadow side is still dark, and the lit side is burning orange-red against a sky that is going from black to deep blue to pale gold, it looks like a painting, not like a photograph of a painting, like an actual painting, like something that could not possibly be real, like something someone invented, rather than something the wind built grain by grain over millennia. At the base of some of these dunes, in the great flat clay pans called vleis, there are dead trees. The most famous of these is Deadlie, a white clay pan surrounded by the highest dunes in the area, filled with the black skeletons of camel thorn trees that died approximately 900 years ago when the Tsauchab River changed course and cut off the water supply to this pan. The trees died. The dunes surrounding the pan prevented the sand from covering them. The air of the Namib, so dry that it essentially arrests the processes of rot and decay, preserved the wood in a state of desiccation so extreme that the trees did not decompose. They simply dried. And they have been standing there, black and bare and skeletal, for 900 years, in a landscape of white clay and orange sand and blue sky, looking like something from the end of a world, rather than something from the middle of ours. This is what the Namib does with time. It preserves things that should be gone. It holds on to the past in a way that wetter places cannot, because rot and decay and the biological processes that return dead things to the soil all require water, and there is almost none here, and so the desert becomes a kind of archive. The footprints of ancient animals in dried mud pans that have not seen water in decades. The remains of shipwrecks on the Skeleton Coast, preserved in the dry salt air, rusting slowly, but still recognizable as ships, sometimes still with their cargo or their gear. The bones of the animals that did not survive the crossing of the desert, bleached and dry, but so perfectly preserved in their arrangement that you can sometimes tell exactly how the animal died, exactly where it fell, exactly what happened in its last moments. The Skeleton Coast. I need to talk about the Skeleton Coast, because this is the place where the Namib becomes the killer in its most concentrated and most spectacular form, and it is the place where the name of this story becomes most literally true. The Skeleton Coast runs along the northern stretch of the Namibian coastline, from the Ugab River in the south to the Kunene River on the Angolan border in the north. The name is believed to come from the Bushmen, who called it the land god made in anger, and from the Portuguese sailors, who called it the gates of hell, and from the accumulated experience of every person who ever tried to navigate this stretch of coastline or cross this stretch of land and found out, often fatally, exactly what it was willing to do to them. The Skeleton Coast is where the Benguela Current, that cold Antarctic water, is most extreme in its effects. The ocean here is not simply cool. It is shockingly, dangerously cold for its latitude, cold enough to produce sea fog so thick that the coastline effectively disappears for hours at a time, cold enough that sailors, using dead reckoning navigation before the age of GPS, had no reliable visual landmarks for stretches of hundreds of kilometers, cold enough that the combination of fog and hidden offshore reefs and the violent surf produced by the prevailing southerly winds made this one of the most treacherous coastlines in the world for sailing vessels. The wrecks began accumulating early in the age of European maritime exploration, and they never really stopped. There are documented shipwrecks on the Skeleton Coast spanning more than 5 centuries, from the early Portuguese vessels whose crews, if they survived the wreck, faced the almost equally fatal prospect of being alive on the Skeleton Coast with no water and no shelter and no realistic chance of rescue, to 20th century ships that ran aground in the fog before satellite navigation changed the equation. The bones that gave the coast its name are not only human. The beaches of the Skeleton Coast are littered with the skeletal remains of whales and seals and seabirds, because the cold, nutrient-rich Benguela Current makes these waters extraordinarily productive for ocean life, which means that enormous populations of marine mammals concentrate here, and with them the predators and the storms and the hazards of life in a cold ocean. And the bones of the animals that do not survive wash up on these beaches in quantities that are hard to fully imagine until you are standing on one of these beaches and you understand that the sand itself seems to be made of bone fragments, fine and white, and ground down by the surf until they are indistinguishable from the mineral grains around them. The largest Cape fur seal colony in the world is at Cape Cross on the Skeleton Coast. Somewhere around 100,000 seals, though the population fluctuates, haul out on this stretch of beach and the adjacent rocks in a density that is, from a distance, incomprehensible to the human eye, because the brain cannot easily process what it is seeing. The beach is simply brown and moving, and loud, an undifferentiated mass of bodies, until you get close enough to see the individuals, and then the scale reasserts itself, and you realize that what you took for a brown blanket on the beach is actually individual animals, each one a living, breathing creature, with its own position in the social hierarchy of the colony, each one representing a successful navigation of the Skeleton Coast's demands, for the moment. Because the desert takes the seals too, not in the way it takes the land animals, not through heat and thirst, but through the particular cruelty of the gap between ocean and land. The seal colony exists at the edge of the Namib, at the precise interface between the extraordinarily productive cold ocean and the extraordinarily hostile dry land. And the pups born on that beach spend their early lives in a state of vulnerability that the desert exploits with a kind of impersonal efficiency. The pups cannot enter the ocean until they have developed their swimming skills and their waterproof fur, and during that period, they are on land, in the heat and the wind, dependent on their mothers for everything, and the mothers must go to sea to feed, leaving the pups on the beach. And sometimes, in the chaos of a colony of 100,000 animals, a mother does not find her pup when she returns. A pup that is separated from its mother in a colony of that size is effectively lost. It will walk, it will call, it will wander deeper into the colony, getting further from the water, getting weaker, calling for a mother who cannot hear it or cannot locate it, and then it dies on the beach of the Skeleton Coast, within sight of the ocean that would sustain it if it could only reach it and survive in it. Brown hyenas patrol these beaches. Black-backed jackals work the edges of the seal colony with a patience and intelligence that is extraordinary to watch, testing the edges of the herd for weakness, looking for the pup that has strayed or the animal that is compromised. The lions of the Skeleton Coast, a population genetically distinct from other Namibian lions and adapted in ways that no other lion population has needed to adapt, have learned to hunt seals on the beach, which is something that sounds straightforward until you try to imagine what it actually requires of a lion to make that work. A seal on the beach moves poorly compared to most of the prey that lions have evolved to hunt. But the beach itself, the soft sand, and the surf, and the noise of the colony, and the specific physics of hunting in a place where your footing is uncertain, changes the calculation in ways that took many generations of coastal lions to figure out. The Skeleton Coast lions are teaching their cubs to hunt in a way that no other lions in the world teach their cubs, in a landscape that no other lions in the world inhabit. And the knowledge of how to survive here is passed from generation to generation in a tradition as specific and as culturally distinctive as the carving traditions of a rock village or the water management traditions of a Kianat community. Let me take you inland now, away from the coast and into the desert itself, because the full horror and the full wonder of the Namib is not just on the coast. It is in the silence of the interior, in the gravel plains and the isolated mountain ranges, and the dry riverbeds that run for most of the year without a drop of water, and then, after a storm in the mountains far to the east, run briefly and violently, and then are dry again, the water absorbed into the sand almost as fast as it arrived. The ephemeral rivers of the Namib are one of its most important features and one of its most misunderstood ones. They look, from the air or from the ground on a dry day, like long scars across the desert landscape, pale lines of sand cutting through the gravel plains, marked by lines of trees, particularly camelthorn acacias and anna trees, that grow along their banks. The trees are there because their roots reach down into the riverbed and access the water that is stored in the sand, the subsurface flow that continues long after the surface has dried, percolating slowly through the sand in the riverbed. These trees are drinking from an underground river that the surface gives no indication of. They are rooted in sand that looks identical to all the surrounding sand, but is in fact a reservoir, a slow-moving body of water that is traveling through the earth rather than across it. The elephants of the Namib know this. The desert-adapted elephants of northwestern Namibia, another population that is genetically distinct and behaviorally unique, and represents one of only 2 populations of desert elephants in the world, the other being in Mali, have learned to find and dig for this subsurface water. They locate the riverbeds. They identify specific spots within the riverbeds where the water table is closest to the surface, and they dig with their feet and their trunks, excavating holes that can be a meter or more deep until they reach water. They then use their trunks to probe the hole and extract water and drink. And after they have drunk and moved on, the holes they have dug remain, and they become water points for all the other animals in the area, the jackals and the springbok and the birds and the smaller creatures that could not dig for themselves but can drink from the excavation that an elephant left behind. This is a form of ecosystem engineering. The elephants are not just surviving in the desert, they are modifying it, creating resources that other species depend on. The knowledge of where to dig, which specific spots in which riverbeds are most productive, is not instinctual. It is learned. It is passed from elephant mothers to their calves through years of observation and practice. And the calves who learn it earliest and most thoroughly have a survival advantage that compounds over a lifetime. The elephant families of the Namib carry a cognitive map of their range, a mental geography of water sources and food patches and dangerous areas and safe corridors. And this map is one of the most valuable things a young elephant can inherit from its family. Lose the family, lose the map, lose the knowledge of how to survive in this desert. And an elephant alone in the Namib is in a very different and much more dangerous situation than an elephant that knows where to dig. The desert-adapted elephants of the Namib are smaller than their savanna counterparts, with larger feet for walking on soft sand and more slender bodies, and they travel extraordinary distances between water and food in a landscape where both are scattered widely. They have been documented traveling up to 200 kilometers in search of water during the dry season, covering distances in days that would take a human weeks. They navigate this landscape at night to avoid the worst of the daytime heat, which can be lethal to an animal, generating as much body heat as an elephant. They rest in the shade of rocky outcrops and dry riverbanks during the midday hours. They drink for days after finding water, rehydrating to a degree that would be dangerous in many other animals, because they have evolved the physiological capacity to tolerate the extreme swings between dehydration and full hydration that their environment imposes on them. There is a moment, which has been witnessed by researchers who have spent years studying these elephants, when a desert elephant that has been walking for days without water finally reaches a water hole or a digging site and begins to drink. The animal does not rush, it stands quietly. It drinks slowly and steadily for minutes. The other members of the family arrange themselves around the water source in order of social precedence, the oldest females first, then the younger adults, then the juveniles, then the calves, who often simply walk into the water and stand in it if it is shallow enough. The relief is visible. It is not anthropomorphism to say that relief is what you are watching. It is just the observable physical behavior of animals that have been severely stressed by deprivation, suddenly having that stress removed. They drink, And then they stand together in the quiet of the desert afternoon, and for a moment, the Namib seems to have relented. And then they move on, because the Namib never actually relents, and the next water source is somewhere out across the gravel plains, and the knowledge of where it is and how to reach it is the thing that will keep them alive until the rain comes, or until it doesn't. I want to talk about the plants now, because the plants of the Namib are where the story of survival under extreme conditions becomes, for me, the most philosophically interesting. Animals can move. They can respond to their environment in real time. They can walk away from danger and walk toward resources. Plants cannot do any of these things. A plant is fixed. It is exactly where it is, in exactly this amount of soil and this amount of sunlight and this amount of whatever moisture the air or the ground provides, and it must survive there, or it must not survive at all. And the plants of the Namib, fixed in one of the driest places on Earth, have solved the problem of surviving in their specific fixed locations, in ways that are so extreme, so unlikely, so genuinely strange, that they have become the subject of serious scientific study and genuine scientific wonder. The Welwitschia is the most extraordinary of them, and I am going to take some time with the Welwitschia, because it deserves time, because it is one of those organisms that once you truly understand what it is, and how it lives, and how long it has been living, changes the way you think about living things in general. Welwitschia mirabilis. The name means wonderful in Latin, which was the reaction of the Austrian botanist Friedrich Welwitsch when he first encountered it in Angola in 1859 and allegedly dropped to his knees in front of it, overcome. He is reported to have written that it was the most wonderful plant ever brought to Europe, and that he could not find words to adequately describe it. This is not the hyperbole of a man who has not seen many plants. Welwitsch was a professional botanist who had spent years in Africa collecting and cataloging specimens. When he said this plant was the most wonderful thing he had ever seen, he meant it, and he was right. The Welwitschia looks, at first glance, like something that is already dead. It looks like a stump, a low, broad, woody stump sitting on the desert floor, usually covered in dust, often half buried in sand, surrounded by what appears to be a heap of long, tattered, leathery straps that curl and twist and dry in the desert sun. It looks like wreckage. It looks like the remains of something, not the living thing itself. But the straps are leaves. They are, specifically, 2 leaves, just 2, growing from opposite sides of the central woody crown, and they grow continuously for the entire life of the plant, which is the thing that takes a moment to process. The Welwitschia grows 2 leaves, and then it grows those same 2 leaves forever, splitting and fraying and tearing as the desert wind and the sand and the years work on them, so that what looks like a heap of many leaves is actually 2 leaves that have been growing and accumulating and fragmenting for a very long time. The oldest Welwitschia plants have been radiocarbon dated at over 2,000 years. The oldest specimens, the great ancient individuals that grow in the central Namib, are almost certainly older than the birth of Christianity, older than the fall of Rome, older than most of the civilizations that most people in the school system spent most of their time studying. These plants have been growing their 2 leaves, continuously, for 2,000 years. They were alive and growing in the same spot when the Roman Empire was at its height. They were there before the Sahara was as large as it is now. They were there before the Norse had discovered North America, and they will likely be there after most of the things we currently consider permanent have changed beyond recognition. The Welwitschia gets its water from the fog. Its broad, flat leaves, which can be several meters long in the oldest individuals, are covered in stomata, the pores through which plants exchange gases with the atmosphere, and these stomata, in the Welwitschia, are also capable of absorbing water from the air. The plant essentially breathes in the fog. When the morning marine layer rolls in off the Atlantic, the Welwitschia opens its stomata and takes in moisture directly from the air, bypassing the need for rain entirely. Its roots go deep into the desert gravel, but the evidence suggests that the roots are for anchoring as much as for water uptake. The water comes from above, from the air, taken in through the leaves. The Welwitschia also has a pollen dispersal strategy that is as strange as everything else about it. It produces cones because it is a gymnosperm, an ancient lineage that predates the flowering plants by hundreds of millions of years. The pollen of the Welwitschia is designed to be carried not by bees or butterflies or other pollinators that most people associate with plant reproduction, but by a specific genus of true bugs, Probergrothius, insects that feed on the plant's nectar, which the Welwitschia produces in quantities unusual for a gymnosperm, essentially mimicking the strategy of flowering plants to attract pollinators while remaining fundamentally, phylogenetically, a cone-bearing plant of a lineage so ancient that it has no close living relatives. It is a survivor not just of the Namib Desert, but of deep evolutionary time, a lineage that once stretched across the Jurassic world and has since dwindled to this single species, living in this single desert, doing what it has done since the dinosaurs were alive, in ways that have not changed substantially in tens of millions of years. There is a stand of Welwitschia in the Namib-Naukluft National Park called the Welwitschia Plains, where hundreds of individual plants, ranging from young specimens a few hundred years old to ancient ones approaching 2,000 years, grow across a stretch of gravel desert that is otherwise almost devoid of plant life. Walking among them is an experience that I struggle to describe in a way that does it justice, because the intellectual and emotional effect of being surrounded by 2,000-year-old organisms that look like wreckage but are alive, profoundly and persistently alive, is not something that translates easily into language. You are in the presence of genuine antiquity, not the antiquity of a building or a ruin, which is the antiquity of something that was made and then stopped and has been deteriorating ever since. This is the antiquity of something that has been continuously, uninterruptedly alive, metabolizing, reproducing, responding to its environment, for longer than most human concepts of history extend. The Namib has also produced, in the animal kingdom, a range of adaptations to the sand itself that are as remarkable as the water-collecting strategies of the beetles and the fog-drinking behavior of the chameleon. Sand is a medium that presents specific physical challenges to movement, the way it shifts under weight, the way it heats to extreme temperatures at the surface during the day, the way it reflects and traps and focuses sunlight in ways that make the thermal environment at ground level very different from the thermal environment even a few centimeters above. The Namib golden mole is one of the most remarkable answers to the challenge of sand. This small, blind, virtually eyeless insectivore moves through the sand the way a fish moves through water, swimming rather than burrowing in the conventional sense, using a fluid, undulating motion to displace sand as it moves through the substrate. It is navigating a world of complete darkness in 3 dimensions, using an enlarged malleus bone in its inner ear to detect the vibrations of prey moving on or through the sand above it, tracking the seismic signatures of insects and lizards and other small animals through the sand, with a sensitivity that serves as its primary sensory system in the absence of functional vision. The golden mole surfaces, attacks prey, and disappears again into the sand in movements so fast and so fluid that watching it happen is disorienting, because your brain expects a burrowing animal to burrow and a swimming animal to swim, and the golden mole is doing something that is neither and both simultaneously. The shovel-snouted lizard, Meroles anchiatae, has solved the problem of the hot sand at ground level through a behavior so precisely adapted and so specifically purposeful that it looks choreographed. This lizard, which is small and fast and lives on the open sand dunes of the Namib, regularly performs what researchers call a thermal dance. When the sand surface reaches temperatures that would cause tissue damage to its feet, it alternates between raising 2 diagonal legs, one front and one back on opposite sides, while standing on the other 2 legs, and then switching, so that at any given moment, only 2 of its 4 feet are in contact with the hot sand. The elevated feet are held up in the air, out of contact with the surface, cooling rapidly in the ambient air, while the grounded feet are in contact for only a few seconds before they are raised and replaced by the previously elevated pair. The lizard is cycling its feet through a cooling phase and a contact phase in alternation, managing the thermal load on each foot by limiting its exposure time to the hot surface. This is thermoregulation by behavioral engineering, and it is so precisely tuned to the thermal parameters of the sand surface that the lizard can be seen doing it within minutes of the sand reaching critical temperature, switching instantly from normal locomotion to thermal dance mode as the temperature climbs above the threshold. When the temperature goes beyond even what the thermal dance can manage, the lizard dives into the sand, not into a prepared burrow, not into a shelter. It dives directly into the loose surface sand, disappearing in a fraction of a second, vanishing completely from the surface into the cooler layer a few centimeters down, where the sand temperature is dramatically lower, because sand is a poor thermal conductor and the surface heat does not penetrate quickly. The lizard sits in its sand refuge for a few minutes, lets its body temperature drop, and then surfaces again, sometimes immediately resuming the thermal dance if the sand is still too hot for normal standing. The sand-diving gecko, Pachydatylus rangeae, has webbed feet because webbed feet on a gecko in a desert are what happens when the selective pressure of living in a sand environment is applied for long enough. The webbing acts as a snowshoe on soft sand, distributing the gecko's weight over a larger surface area and preventing it from sinking. The same gecko uses its webbed feet to shovel sand over its body when burying itself, and it uses its peculiarly large, wet-looking eyes to hunt moths and other insects that are attracted to moisture at night. The eyes of the web-footed gecko are so large relative to its body size that they give the animal an expression of startled intensity that is, frankly, rather endearing, and which has made it one of those creatures that people respond to immediately and viscerally as adorable, which it is, while also being an engineering marvel of optical sensitivity evolved for hunting in the extremely low light levels of a fog-shrouded desert night. I want to go back to the killing, though, because we started there, and I do not want to let it slip away, because the way the Namib kills is the core of what makes it different from any predator, and understanding that difference is understanding something important about what the desert actually is. A predator kills selectively. A predator picks a target, usually one that is already vulnerable, the old, the young, the injured, the separated. A predator exerts energy to kill. A predator has good days and bad days. A predator has a belly that fills and an appetite that is satisfied, at least temporarily. A predator cannot kill faster than it can eat, and it kills where it is, in its territory, in its range, in the places where it has learned to hunt. The Namib does none of these things. The Namib kills without preference, without selection, without targeting the weak or the young or the compromised. If you are in the wrong place in the Namib, at the wrong time, without the right adaptation, you die. It does not matter if you are old or young, healthy or sick, fast or slow. If you are a species that has not developed the specific toolkit that this specific desert requires, you die. Not because the desert is attacking you, because the desert simply is. And what it is incompatible with your continued existence if you have not adapted to it. This is the thing that makes the Namib more dangerous than any predator, and that makes the death toll it has accumulated over 55 million years of desiccating life incalculable. Every species that wandered into this desert, from the wetter landscapes to the east or the north or the south, without the adaptations it required, either developed those adaptations through evolution, or it died. Most of them died. The ones that survived and adapted, and are still here, are the ones whose ancestors happened to have the random genetic variation that gave them a slightly better capacity to tolerate thirst, a slightly more efficient fog collection surface on their bodies, a slightly better thermal dance, slightly more webbing between their toes. The Namib did not select those